we have a big question. I'm not going to read that out. So pause for a while and try to understand the question, and let's solve it now. Okay, so we have been given that there is a particle which is executing a simple harmonic motion according to the equation x equal to 10 times sine pi t plus pi by 3. And we are asked a bunch of stuff like frequency, time period, and maximum, and blah blah blah. Anyways, before we solve this, we will need some background. We already saw that a simple harmonic motion must follow the differential equation d square x by dt squared, it can be anything, plus omega square x should be equal to 0. That's the defining feature of simple harmonic motion, at least free oscillations of simple harmonic motion. Okay, now what if I wanted to find the solution to this differential equation? Well, I'm not going to do the solution because that's pretty much beyond the scope of the syllabus. It's a second order differential equation. I'm just going to throw the solution at you. We can, intuitively guess what kind of a function must be a solution to this. We already have a question here. Anyways, look, the function should be, when you double differentiate it, it should get the same form as x, because if it doesn't, then it doesn't add up to become 0. So double differentiation should get the negative of that function, some sort of a function like that. So the function which, after double differentiating, it comes back to the original. And those functions are trigonometric, and usually it's sine and cos. You differentiate sine, you get cos. You differentiate cos, you again get sine with a negative sign, right? Same thing with cos. You can also go for exponential functions, but exponential functions will require some complex planes and stuff like that, so we will not look at exponential solutions. So the solution that we have usually is a cos and a sine. Anyone will do. So in general, we'll write the solution as x equals a, let's say sine omega t plus phi. I'm going to first explain what these things are, and then we'll tackle this problem a little bit later. So a is basically the maximum value of x, right? Can you see that? So maximum value of x is a, and which we call as the amplitude. Here is the amplitude. So basically what I'm trying to tell you is, if you have a particle that's oscillating from the mean position, this is the mean position, let's call this as x equal to 0, okay? It's going to oscillate all the way, it's going to go all the way over here, and it's going to stop, right? It's going to go all the way like this and stop and then turn back. This distance is what we call as a. That's the amplitude. It's going to come back, come all the way over here. Again, this distance is called as amplitude. So one direction we'll call it as positive a, one direction we'll call it as negative a, and that's the maximum displacement it's going to have from the mean position. That's this a, amplitude. Okay, this whole thing inside, omega t plus phi, is given a name. It's called as the phase angle. And these names are important because I'll be using these names. Phase angle, as the name suggests, is just the angle. And phase angle, I already told you what this phase business is, right? You imagine that, simple harmonic motion is a circular motion, and then that angle covered is what is called as the phase angle. Okay, so that's the whole thing inside. Omega is something we already know. It's the angular frequency. We discussed that. Phi is what is called as a phase constant. Phase constant. And this phase constant basically is telling you about the initial conditions. Actually, these two guys, amplitude and the phase constant, they both depend on initial conditions. So these guys depend on, not like this. This guy does not depend on. So let me just write that down. A and phi depend on initial conditions. Okay, initial conditions. And the omega value doesn't depend on the initial conditions. We saw in so many cases omega depends only on the property of the system, only on property of system, which means if I have a spring of spring constant k and mass m, bang, its omega is fixed. Then whether I stretch it a little bit or I stretch it more, it doesn't depend on the displacement. Okay, it doesn't depend on the initial conditions. So that's what I mean by initial conditions. Initial conditions are, we have two options. We have two things to choose. One is we can choose what's this displacement. So if you want, the displacement can be whatever you want. And we can also choose, the second one is the velocity with which we're going to start that. We can give the velocity as 0, or we can punch it or kick it in this side. So you choose always displacement and you choose initial velocity. These two things are going to reflect in your amplitude and phi values, okay? But omega omega only depends on the property of the system, and it doesn't depend on the initial condition. It's not very intuitive, but remember, if you have a spring, you stretch it a little bit or you stretch it more, the omega will remain the same, provided the masses and the spring constants are the same, okay? All right, with that in mind, we can now tackle this problem. One last thing. It doesn't have to be of this particular form. It doesn't have to be a sine. It can be a cosine. Even cosine is fine. This can be positive, this can be negative. Basically, any equation of the form which has sines and cosines, or even combination of sines and cosines, which by the way we'll look at a little bit later, but any of those things will work, okay? Provided they should have the same sort of phase angle. Anyways, all right, so sines and cosines. Okay, let's go back to this now. We have to first figure out what the frequency and time period are by looking at this. Well, let's compare this with our standard equation. A sine, whatever comes with t is omega. So omega t plus pi by 3. So omega must be equal to pi. Since omega is pi, 2 pi f is pi. Pi cancels. We now have f. F is equal to half. So we got the first answer. The frequency is half hertz. Okay, we also need the time period, and time period is just the reciprocal of the frequency. That's 2 seconds. So that's easy. That's done. Okay, next thing we want to calculate is we need to calculate the velocity at some different moments in time. Okay.